A gear is similar to a pulley, but it has a series of teeth around the perimeter of the wheel. The teeth on two gears fit together, allowing one gear to turn the other. Simple gears like these ones are called spur gears. Their axles, the bolts through the center, are parallel. Notice that when I rotate the large gear clockwise, the small gear rotates the other way, counterclockwise. Gears can change the direction of rotation. Gears can also change the rate of rotation. Let's rotate the large gear once and count how many rotations the small gear makes. Did you get 2? Rotating the large gear once causes the smaller gear to rotate twice. The small gear also rotates twice as fast as the big gear. The big gear has 40 teeth. How many teeth do you think the small gear has? Remember that the small gear turns twice as fast as the big one. If you estimated 20, you're right. The big gear has twice as many teeth as the small one. You can determine the rates of rotation of two gears by comparing the number of teeth on each one. Can you see the different rates of rotation in these gears? The smaller gears rotate faster than the big gears. Spur gears are often joined on the same axle, creating a compound gear. Compound gears provide even more options for controlling rates of rotation. Some gears are able to connect at an angle. These are bevel gears. These bevel gears are connected at a right angle, or 90 degrees. Gears can be used in machines to increase force. Engineers call this increase in force mechanical advantage. These machines usually have a small gear driving a big gear. Machines using gears control these locks. Locks are a special system of gates located in a river or canal system that are designed to move boats up or down. This system joins the Ottawa River to the Rideau Canal, and it moves ships up or down a total of 24 meters. The process is controlled by human muscle, assisted by a winch. A hand-operated winch is a machine that combines gears with a crank and chain or cable to create a large mechanical advantage. Here's how these locks work. A boat moving from the Rideau Canal down to the Ottawa River starts at the top. It is in a gated enclosure filled with water. The water flows out of this first chamber until it is at the same level as the next chamber. At this point, a winch is used to open a huge pair of gates, and the boat moves into the next chamber where the process repeats until it is at the bottom and into the Ottawa River. This set of gears, powered by human muscle, is moving the massive gate so the boat can travel to the next level. Notice a small gear is turning a big one, a ratio that provides a significant mechanical advantage. This machine includes a crank and drum to wind the chain onto. These also increase the mechanical advantage of this machine. A human without this machine could not produce enough force to move the gates. Gears make this possible. If you own a bicycle, you have a machine with a very sophisticated gear system. The gears on a bicycle don't mesh directly like the gears we were looking at a few minutes ago. These gears are connected by a chain. Gears that are connected by a chain have a special name. They're called sprockets. We have a sprocket on the front here that's connected to the pedals. We have a pedal arm. We can create some force to start moving that chain. And on the back, we have another sprocket connected to the rear wheel. Turning the pedals moves the rear wheel. You'll notice that the pedals and the wheel move in the same direction. That's how a system like this works. We have two sprockets in one chain. Everything rotates in the same direction. Some bicycles allow you to change gears. We know that if you use gears with different numbers of teeth, you can change the rate of rotation. Well, this bicycle has 3 sprockets on the front and 5 on the back, giving you a total of 15 different combinations of gears that you can use here. I've just set this up so that I'm on the back sprocket, the one closest to me, and I'm on the back sprocket here at the back wheel. They both have exactly the same number of teeth, and when I rotate, I'm going to rotate the pedal all the way around once. We make one rotation of the wheel with every rotation of the pedal when the sprockets have the same number of teeth. Here, I'll just do that again. Notice we've got our red marker here and a pedal there. And I'll just rotate all the way around to there. And we stop right there. The number of rotations are equal at each end. This gives you a good mechanical advantage. It makes it easier to bicycle up hills, for instance, and get started. Bicycles are complicated. There's also some mechanical advantage from the pedals, the length of the pedal arms, the size of your rear wheels, and so on. All influence the mechanical advantage here. Let's change our gears for speed. Now to do that, we have some levers on the handlebar that I can use to actually move the chains. Now I've moved our front chain. It's on a sprocket with 48 teeth, and on the back chain we're on a sprocket with 14 teeth. Let's look at our rotations now. I'll line up the pedal, and we've got our red marker here, and I'll start turning. Our wheel's gone once. Wheel's gone twice. 3 times. And when the pedal's back to its start position, we've actually made about 3.5 revolutions with that back wheel. This gives us lots of speed. Professional bicycle racers use sophisticated gearing systems designed to produce maximum power and speed. Gears represent an ancient technology that we continue to find new and exciting uses for. The gears in this sophisticated robotic arm, the Canadarm, provide precision control and significant mechanical advantage. Orbiting the Earth, this powerful arm is being used to construct the International Space Station. If you are teaching an introductory unit on gears or just interested in learning more about them, you may want to construct a gears workstation. To do this, I purchased a bag of gears from Spectrum Educational Supply in Newmarket, Ontario. Similar products are available from most science supply retailers. A 3/16" bolt works well as an axle, and properly spaced holes drilled in a board allow you to investigate various gear relationships. I also glued different size gears together to create compound gears. Another good teaching tool is a clock mechanism. Our video Time Clocks and Gears includes a demonstration with a clock kit. To view this video, follow the video link at our website, hylaroad.com.